Welcome back to the deep dive. Today we are really channeling our inner elemental mastery. We're talking about turning you into a true data bender, someone who can shape data, control its flow, make it do what you need it to do.
Exactly. And that journey, that mastery, it really starts with data modeling. It sounds basic, but it's critical, especially if you're aiming for those tougher data engineering roles,
Yeah.
system design interviews.
Right. They don't just want definitions. They want strategy. They want to hear why you'd pick one model over another, what the trade-offs are.
Precisely. Knowing the what isn't enough.
Uh,
It's the why and how that matters architecturally.
So we've cracked open the books, the academic stuff, Kimball's industry standards, complex system design patterns, all of it.
Yeah, quite a stack.
And our mission today is to pull out that core knowledge, the stuff you need to confidently answer that big question. Okay, how do you model this system? And answer it thinking about scale, history, performance, the whole picture.
It all starts with a good analogy, I think. If data is your, say, building material.
Then the data model is the blueprint, the detailed plan.
Exactly. It dictates everything, foundation to the roof. It's not the building itself, but the design for it.
And that brings up two key ideas right away. Schema versus instance. The schema is that blueprint, isn't it? It's the structure, the rules tables, columns, constraints, fairly stable, ideally.
Right. It's the definition. While the database instance, or the state, that's the actual data filling the structure. That changes constantly, transaction by transaction.
Yeah.
The real world is messy. Data reflects that.
So schema, plan, instance equals current reality.
Got it. Okay, let's unpack this blueprint idea. It's not just one drawing, is it? It's more like a process, layers.
That's a great way to put it. It's a progression. 3 distinct layers, really, to make sure you go from the business need all the way to the technical spec without jumping the gun.
So layer 1.
That's the conceptual model. Think high level. It's completely technology independent. We're just talking business concepts here. Customers, products, orders. What are the main things? And how they relate to each other. Like one customer can have many orders.
Exactly. One to many, many to many. Just capturing those core business entities and relationships. Often using something like an entity relationship or ER model. It's about understanding the business, not the database yet.
Okay, pure business logic. Then what's next?
Then you get a bit more technical with the logical model. This is the bridge. You start mapping those conceptual things to actual structures. We define data types as a string, an integer, a date.
And defining keys. Like this is the primary key for customer.
Precisely. Primary keys, foreign keys to link tables, figuring out those relationships in more detail. But, and this is important, you're still not tied to a specific database system, like Oracle or Postgres or whatever. It's logical structure, not physical implementation. Analysts, architects usually own this part.
Takes sense. So conceptual is the idea, logical is the detailed plan, and then?
Then you hit the ground with the physical model. This is implementation reality. How is this data actually going to be stored? What are the exact table names, column names, data types in our chosen database?
So this is where specifics matter, like indexing strategies.
Absolutely. Indexing, constraints as enforced by the specific database, partitioning strategies for performance. This is where the database administrators and data engineers really get into the weeds, optimizing for the actual hardware and system. Hashtag tag 1.2 essential modeling terminology.
Okay, to build these models, these blueprints, we need the right tools. You mentioned models come with languages.
Yeah, they do. The blueprint itself, the schema definition, you create that using DDL, data definition language.
That's like the create table statements in SQL.
Exactly. It defines the structure. The database compiler takes that DDL and builds the empty tables, sets up the constraints. That's the foundation.
And then to actually use the database, put data in, get it out.
That's DML, data manipulation language. Your select, insert, update, delete statements. That's how applications and users interact with the data within the defined structure.
Okay, DDL defines, DML manipulates. Got it. You also mentioned transactions earlier. How do they fit in?
Transactions are fundamental for reliability.
Yeah.
A transaction is basically a single unit of work, maybe fetching some data, maybe updating it. The key rule is atomicity.
Meaning?
It has to succeed completely, making a permanent change, or it has to fail completely, leaving the database exactly as it was before. All or nothing. No partial updates allowed. Think about transferring money. You can't debit one account without crediting the other. That's atomicity.
Right, that prevents inconsistencies.
Mm.
Which brings us to constraints. These are the rules embedded in the model.
Exactly. They enforce the data's integrity, make sure it
Mm-hmm.
reflects the real world, or at least the business rules.
Mm-hmm.
And there are different kinds.
Okay.
You have inherent constraints, which are just part of the model itself. Like in ER, a relationship has to connect entities. It's built in. Then implicit constraints. These are things you specify in DDL that the database enforces automatically. Like saying a column cannot be NaOL, or defining a foreign key relationship.
Okay, so database level rules.
Right. But then you get the explicit or application-dependent constraints. These are often more complex business rules. Things that are specific to this application's logic may be too complex for standard DDL.
Like what? Give me an example.
Maybe a rule like a premium customer's discount can never be lower than 10% unless approved by a manager. That logic might live in the application code, not just the database schema.
Okay. More nuanced. And you also mentioned dynamic constraints. These sound tricky.
They are. They're about changes in state, not just the state itself. The classic example is an employee's salary can only ever increase.
Wait, yeah, how do you enforce that? A simple check constraint in SQL usually only looks at the current rows data, right? It doesn't know the previous value.
That's the challenge. Standard DDL is mostly for static checks.
Yeah.
So dynamic constraints like that often have to be enforced either in the application layer, the code checks the old salary before allowing the update, or using database triggers. A trigger is code that runs automatically in the database on an event, like an update. It can look up the previous state or related data to enforce the rule, but triggers can be complex, harder to manage, and can impact performance.
So recognizing when a rule is dynamic versus static tells you where and how it needs to be enforced. That's a key design decision.
Absolutely. It shows you're thinking about the implementation implications, not just the rule itself.
You also mentioned fragmentation briefly as a way to manage scale, like partitioning.
Yeah, fragmentation or partitioning is a classic technique, especially for large tables. Two main types.
Horizontal and vertical.
Right. Horizontal partitioning splits the rows. Maybe you put all 2023 orders in one partition, 2024 in another, or maybe partition by region, North America here, Europe there. Queries that only need recent data, or data for one region, only scan a smaller piece, much faster.
And vertical partitioning.
That splits the columns. If you have a huge customer table, but most queries only need name and email, you might split off less used columns like detailed demographics into a separate table. Again, the main queries hit a smaller, faster table. It's all about optimizing access paths.
Okay, so we have these modeling layers and terms. Now, the big fork in the road. Are we building a system primarily for handling transactions, lots of writes and updates, or for analysis, lots of complex reads, OLTP versus OLA?
That's the fundamental strategic choice. It dictates your entire modeling approach. For OLTP, online transaction processing, think banking systems, e-commerce checkouts, operational stuff. The king is normalization.
Right. The goal there is all about organization, minimizing redundancy, making sure data is consistent when you write it. Hashtag tag 2.1 normalization, the OLTP writing focus.
Exactly. Normalization is this step-by-step process to reduce data duplication and potential inconsistencies. It starts with first normal form, 1 and F.
Which means?
Two basic rules. First, every cell has a single atomic value. No storing multiple phone numbers in one field, for example. Second, every row needs a unique primary key. Simple foundation.
Okay, then, second normal form, 2NF.
2NF kicks in when you have a composite primary key, a key made of multiple columns. The rule is, every non-key column must depend on the entire primary key, not just part of it.
Let's use your flight example. Key is flight number, seat number. If I put aircraft model in that table...
You've broken 2NF, because aircraft model depends only on the flight number, not the combination of flight and seat. You'd have the same aircraft model repeated for every single seat on that flight. Redundant.
So you pull aircraft model out into a separate flights table, keyed just by flight number.
Precisely. You eliminate that partial dependency.
And the big one everyone talks about, third normal form, 3NF.
Right. You have to be in 2NF first. 3NF tackles transitive dependencies. This means a non-key attribute shouldn't depend on another non-key attribute.
The classic example is location data, isn't it? Employee table has zip code, which determines state, which determines region.
Exactly. State depends on zip code, and region depends on state or zip code.
Yeah.
Those are transitive dependencies, because state and region aren't part of the employee's primary key. 3NF says you should move zip code, state, and region into their own locations lookup table.
Why? What's the practical pain of violating 3NF? People ask this in interviews.
It creates update anomalies. Imagine the Postal Service realigns states for a zip code. If state is in the employee table, you have to find and update every single employee record with that zip code. Miss one, and your data is inconsistent.
Ah, but if it's in a separate locations table.
You update it in one place, just the single row for that zip code in the locations table. Normalization protects data integrity during writes and updates. That's its primary purpose.
Makes total sense for operational systems. But like you said, there's a cost when you want to read that data back, especially for analysis.
Huge cost, because to get a simple view, like a customer's name, their city, and their last order total, you might have to join the customer table to the address table, which joins to the locations table, and also join to the orders table. Lots of joins.
And joins are computationally expensive, right? They slow down queries.
Severely,
Yeah.
especially with large tables. So highly normalized structures are generally pretty bad for direct analytical querying or reporting. You're optimizing for writes at the expense of reads. Hashtag tag 2.2 semantic models, the conceptual bridge.
Okay, but before we jump straight to fixing the read problem, let's quickly revisit that conceptual phase. You mentioned the entity relationship ER model. Why is that still important if it's not the final database structure?
Because it captures the meaning, the semantics, much better than just a set of tables and foreign keys.
How so? You mentioned the flatness of the relational model.
Right. In an ER diagram, you literally draw a line and label it employee or for some department. That relationship is explicit, clear business language. In the relational tables, it's just a departmented column in the employee table. The link is implied, not visually represented. ER models are fantastic for communication, for making sure everyone understands the business structure before you get technical.
So it's a crucial communication and design tool, even if the final implementation looks different.
Absolutely vital, especially when dealing with complex relationships. Which brings us to the classic problem, many-to-many M2M relationships.
Like students and courses. One student takes many courses, one course has many students.
Exactly. You can't directly model that with just a foreign key in either the student or course table. It violates relational principles.
So what's the fix? This comes up all the time.
The fix is standard. You introduce an associative entity, sometimes called a bridge table or junction table.
Walk me through that for students and courses.
You'd create a new table, maybe call it enrollment. Its primary purpose is to connect students and courses. It must contain foreign keys pointing back to both the student table, student ID, and the course table, course ID.
So each row in enrollment represents one specific student enrolling in one specific course.
Precisely. It resolves that relationship into two one-to-many relationships. One student can have many enrollments, and one course can have many enrollments.
And the primary key for enrollment is usually just the combination of student ID and course ID.
Often, yes. The composite key student ID, course ID, uniquely identifies an enrollment, unless the enrollment itself needs its own attributes, like the enrollment date or the grade received.
Ah, okay. If the relationship itself has properties.
Then the enrollment table might get its own unique ID, a surrogate key, and the student ID and course ID become just foreign keys, allowing you to store those extra attributes like grade or date cleanly. But the core idea is, needs that bridge table. No way around it in relational databases. Hashtag 2.3 dimensional modeling, the OLAP reading focus.
Okay, so normalized is great for writing, but bad for reading. When the goal is analysis, reporting, business intelligence, OLAP, online analytical processing, we need a different approach.
Completely different. We pivot to dimensional modeling, heavily influenced by Ralph Kimball. And the key philosophical shift is embracing denormalization.
Intentionally adding redundancy. That sounds wrong after everything we just said about normalization.
It does, but it's purposeful redundancy. We denormalize specifically to make queries faster by reducing the number of joins needed. Performance for reads is the priority here.
So how is it structured? You mentioned two main table types.
Right. At the center, you have fact tables. These hold the numbers, the measurements, the metrics you want to analyze, like sales amount, quantity sold, costs. They also contain foreign keys pointing to the dimension tables.
And the context for those numbers comes from?
The dimension tables. These surround the fact table. They provide the descriptive context, the who, what, when, where, why behind the facts. Think tables for time, product, customer, store, etc. They contain attributes like product name, customer city, calendar date.
And these dimension tables are where you filter or group your data in reports, like show me sales by product category for last quarter.
Exactly. Dimensions are the primary source for query constraints, the where clause, groupings, the group by why clause, and the labels on your reports.
And when you arrange them central fact table, surrounding dimension tables, that visual structure is the star schema.
That's the classic fundamental dimensional structure. One big fact table in the middle connected directly to multiple dimension tables radiating outwards, like points on a star. It's simple, intuitive, and crucially, it minimizes joins for typical analytical queries. You usually just join the fact table to the dimensions you need. Much simpler and faster than navigating a complex normalized structure.
Okay, let's get deeper into dimensional modeling. You mentioned granularity with fact tables. Sounds like getting this right is make or break.
It absolutely is. The granularity is the level of detail captured in each fact table row. What does one row represent? A single sales transaction line item, a daily summary for a store, an hourly snapshot of inventory.
And the rule of thumb is?
Go for the lowest, most detailed level of granularity possible, the most atomic level that your source systems can provide. So, individual transaction line item, not just the total order value.
Why? Storage is cheap, but is that the only reason?
It's about flexibility. You can always aggregate detailed data up. You can sum line items to get order totals, some orders to get daily totals, some daily totals to get monthly totals, but you can never drill down into detail that wasn't captured in the first place.
So if I only store daily sales summaries, I can never analyze buying patterns within the day. I've lost that ability forever.
Exactly. Choosing the grain determines the ultimate analytical capability of your data warehouse. Sometimes source systems limit you, and you have to document that limitation, that loss of potential insight. But always aim for atomic grain if you can get it.
Related to the numbers in the fact table, the measures, is this idea of additivity. What's that about?
It's about whether you can meaningfully sum up the measures across different dimensions. Ideally, measures are fully additive. Sales amount, quantity sold, you can sum those up by time, by product, by store, any way you like, and the result makes sense.
But not all measures are like that.
No, some are semi-additive. A common example is inventory balances or account balances. You can sum inventory levels across different products or different warehouses at the same point in time, but you can't meaningfully sum inventory levels across time. Adding Monday's balance to Tuesday's balance doesn't tell you much.
Right. And then they're non-additive measures.
Yeah, things like ratios, percentages, temperatures, unit prices. You can't sum percentages directly. Adding a 10% profit margin from one sale to a 20% margin from another doesn't give you a meaningful total margin.
So if you have semi-additive or non-additive measures, how do you handle them? Don't store them.
You store the fully additive components that allow you to calculate them. For profit margin percentage, you store the sales amount and the cost amount, both fully additive. Then, the BI tool or query calculates the margin percentage on the fly, sales cost, sales. This preserves flexibility. For inventory, you store the balance snapshot, understanding its semi-additive nature.
Got it. Store the raw ingredients, calculate the complex recipe later.
What about merging facts, combining fact tables?
That's often a good idea if you have multiple fact tables that represent different aspects of the same core business process and share many of the same dimensions. For instance, maybe you have sales orders and sales invoices as separate facts initially.
Why merge them? If they share dimensions like time, customer, product, and you can align their granularity, or choose the lowest common grain, merging them into a single fact table can simplify the model, reduce data redundancy, and allow analysts to easily compare order details with invoice details in a single query. It increases the analytical scope of that consolidated fact. Hashtag 3.2 special types of dimensions and facts.
Dimensional models aren't just standard facts and DIMs. There are some special cases. Let's start with the weirdly named factless fact table. A fact table with no facts.
Yeah, it sounds counterintuitive. But it serves a specific purpose. It records that an event occurred or establishes relationships between dimensions, even when there are no numeric measures to record.
Like what kind of event?
Classic examples. Tracking student attendance in courses. The fact is simply that the student was present on that day in that course. Or tracking which products were eligible for a promotion campaign, even if they didn't sell. Or recording which salespeople called which prospects.
So the table just contains foreign keys back to the relevant dimension tables, like student ID, course ID, date ID.
Exactly. It allows you to analyze the relationships. How many students attended this course, or which promotions were applied to which products. Even without a quantity or dollar amount, it captures participation or eligibility.
Okay, makes sense. Next special case, degenerate dimension. A dimension key stuck in the fact table with no actual dimension table.
Right. Think about operational identifiers like an order number, invoice number, or maybe a shipment tracking number. These numbers are often useful for tracing back to the source system or for defining the exact grain of the fact row.
But they don't usually have other descriptive attributes you'd want to analyze by, like you don't group sales by invoice number usually.
Exactly. There's no need for a separate invoice number dimension table with just the key in it. So the key itself, the invoice number, lives directly in the fact table. We call it a degenerate dimension because it acts like a dimension key for granularity and traceability purposes, but it doesn't have its own dimension table attributes.
Got it. It's there to define the grain. And finally, the essential time dimension. Why do we need a whole separate table for dates? Can't we just use the date timestamp column in the fact table?
You could, but you lose a lot of analytical power and risk errors. A dedicated time dimension table is crucial
Why?
because time has structure and context that a simple timestamp doesn't capture easily. A time dimension table is pre-populated with every day for several years. Each row represents a single day and contains attributes like day of week, month name, quarter, year, fiscal period, holiday indicators, weekend flags, all sorts of useful context.
Ah, so you can easily group or filter by fiscal quarter 3 or all Saturdays without complex date functions in every query.
Precisely.
Ah.
And crucially, it handles complex calendar logic correctly. For example, a week might span across two different months or quarters. A proper time dimension lets you accurately assign facts to the correct reporting periods. Relying on just the timestamp makes slicing and dicing by these business calendar structures much harder and error-prone. It's a foundational dimension in almost every store schema.
Okay, fact tables capture events. Dimension tables describe the context at the time of the event. But dimensions themselves can change over time, right? A customer moves, a product gets rebranded, a sales territory gets reassigned.
Exactly. These are slowly changing dimensions, or SCDs. And how you handle these changes is critically important for historical reporting accuracy. This is prime interview territory.
So what are the main ways to handle it? Let's start with the simplest, type 1.
SCD type 1 overwrite is just that. The new value overwrites the old value. Customer moves. You update the address column in their dimension row. Done.
Simple, but what's the catch?
You lose history. If you run a report on last year's sales after the customer moved, it will look like those sales happened from their new address. The historical context is gone. Type 1 is only suitable for correcting errors or for attributes where history truly doesn't matter.
Okay, so if history does matter, which it usually does for analysis,
Then you need SCD Type 2 new row historical tracking. This is the workhorse, the gold standard for preserving history. When a tracked attribute changes, say, the customer's assigned sales rep changes you don't overwrite.
what do you do instead?
You preserve the original row, marking it as no longer current, and you insert a completely new row for that same customer, containing the new sales rep information and marked as the current version.
So one customer might eventually have multiple rows in the dimension table. How do you know which row was valid when a particular sale happened?
That's the key. You add metadata columns to the dimension table, typically things like effective start date, effective end date, and a isCurrent flag. When the sales rep changes, you set the effective end date on the old row to the date before the change, and the new row gets the change state as its effective start date and a null or far future effective end date.
Ah, so when you join your sales fact table, which has a sale date to the customer dimension, you join not just on customer ID, but also ensuring the sale date falls between the effective start date and effective end date of the customer row.
Exactly. That ensures you always link the sale to the customer dimension attributes as they were at the time of the sale. It perfectly preserves history for accurate analysis. It's more complex to manage, but essential for trustworthy reporting.
What about SCD type 3, new column? I've heard of that too, like having current address and previous address columns.
Type 3 exists, but it's much less common and less scalable. You add a new column to store one specific previous value of an attribute, maybe current sales rep and prior sales rep.
What's the limitation?
It only tracks the most recent change. If the sales rep changes 5 times, Type 3 only tells you the current one and the immediately preceding one. You lose the full history. It's sometimes used for very specific, limited historical comparisons, but Type 2 is the generally preferred solution for comprehensive history tracking.
All right, let's zoom out a bit to broader architectural strategy. Beyond the modeling technique itself, how data flows into the model is crucial. This brings up ETL versus ELT.
This is a huge decision point, heavily influenced by your infrastructure, especially with the cloud. ETL stands for extract, transform, load. Historically, this was the standard.
meaning you pull data from sources, extract, clean it, reshape it, apply business rules, transform, often on a separate dedicated server, and then load the clean, structured result into your target data warehouse.
Exactly. Transformation happens before loading. The data warehouse receives polished, ready-to-use data conforming to a predefined schema. This made sense when compute power in the warehouse was expensive and limited.
But now, with cloud data warehouses like Snowflake, BigQuery, Redshift, Databricks, things have changed.
Dramatically. These platforms offer massive, scalable, relatively cheap compute power within the warehouse or lakehouse environment. This enabled the rise of ELT: extract, load, transform.
So flip the last two letters. Extract the raw data, load it first into the cloud storage, often a data lake, and then use the power of the cloud platform to transform it later.
Precisely. You land the raw, unchanged data quickly. This has advantages. You capture everything up front, reducing the risk of discarding potentially useful data due to premature transformation rules. Transformations can then be done more flexibly, perhaps by different teams for different purposes, directly within the powerful target environment.
So ELT is more flexible, better for uncertain requirements or evolving logic. You store the raw stuff first, figure out the transformations later.
Generally, yes.
Yep.
ETL assumes you know the target structure and business rules quite well up front. ELT embraces agility and leverages powerful cloud compute for transformations after loading. The choice depends on your architecture, certainty of requirements, team skills, and cost model.
Once the data is loaded, especially into those potentially huge fact tables in our dimensional model, performance becomes critical. We touched on partitioning earlier, but let's revisit it in the context of large fact tables.
Yeah, for multi-terabyte fact tables, partitioning isn't optional. It's essential for survival. Horizontal partitioning, usually by date, for example, partitioning by month or year, is the most common and effective strategy.
Because most analytical queries focus on recent time periods.
Exactly. If you query for last quarter's sales, the database only needs to scan the partitions containing those months, ignoring potentially years of older data. This is called partition pruning, and it drastically reduces I/O and speeds up queries. You might also partition by region or business unit if those are common query filters.
Is vertical partitioning still useful for fact tables?
It can be, though less common than for wide dimension tables. If a fact table has hundreds of measures, but most queries only use a small subset, vertically splitting the frequently used measures from the rarely used ones could improve performance by reducing the amount of data read for common queries. It's an optimization to consider.
And then there's indexing. Essential for finding data quickly, but there's a trade-off.
Always a trade-off. Indexes speed up select queries dramatically by providing shortcuts to data. But every index you add slows down insert, update, and delete operations because the index itself also needs to be updated.
So in a data warehouse that gets loaded frequently, maybe daily or even hourly,
You have to be judicious with indexes. Index the columns frequently used in where, clauses, and join conditions, especially the foreign keys in the fact table linking to dimensions. But critically, you need to monitor index usage. It's very common for indexes to be created for specific reports or analyses and then forgotten about.
and those unused indexes just sit there, slowing down data loading.
Precisely. Good data warehouse management includes periodically identifying and dropping unused indexes. It's a balancing act between read performance and load performance. Hashtag 4.3, the critical first step in data modeling. Interview strategy.
Okay, let's talk interview strategy. You get asked a system design question. Design the data model for feature X. What's the biggest mistake candidates make?
Jumping straight to tables and columns. Drawing the physical model immediately. It shows they can think in SQL maybe, but not that they can think architecturally or understand the business need.
So what's the right approach? The three-step path.
It starts way before tables. Step 1. Identify and clarify the business process. What exact process are we modeling? Is it the entire customer journey? Just the checkout part. What's the scope? You need to define the boundaries first.
Makes sense. Get the scope clear. Then step 2.
This is the make or break step. Ask clarifying questions to define the specific metric. Interviewers often give you a vague goal on purpose, like, we want to increase user engagement.
That can mean anything.
Exactly. Your job is not to guess. Your job is to ask questions. What defines engagement? Is it logins per week? Time spent on site? Number of articles read? Number of purchases? For which users? Over what time period? You have to push back and force clarity.
So you might drill down from increase engagement to something super specific, like, okay, the goal is to increase the average number of items added to the cart per active user session.
Perfect. Now you have a concrete, measurable metric.
Yeah.
And that leads directly to step 3. Create the model tables designed to answer that metric.
Ah, the model must directly support the calculation defined in step 2.
Yes. If your final proposed tables don't make it easy and efficient to calculate items added to cart per active user session, then your model has failed, no matter how well normalized or beautifully structured it looks. The model must serve the specific business question you clarified. That's the key insight they're looking for. Hashtag tag tag 4.4 advanced modeling patterns,
Yeah.
handling history and complexity.
To really elevate the design, especially for complex scenarios, there are more advanced patterns. Let's touch on 2. First, building comprehensive historical views, like a master user dimension, using cumulative table design.
Right? This is a powerful technique often used in ETL/ELT pipelines to build tables that track the complete history or the current state of all entities, even those not present in the latest input data. Think mail users or demo products.
How does it work? You mentioned a daily join process.
Yeah, the core logic often involves taking today's snapshot of input data, for instance, today's active users, and doing a full outer join with yesterday's accumulated master table, demo users from yesterday.
Full outer join. So that captures users in both, users only in today's data, new, and users only in yesterday's data, churn.
Exactly. It covers all possibilities.
Yeah.
Then you use the coalesce function strategically when selecting columns for today's output, which becomes tomorrow's input.
How does coalesce help here?
Coalesce returns the first non-null value from a list. So for an attribute you want to preserve from history, like first sign update, you'd write coalesce yesterday.firstSignUpdate, today.firstSignUpdate. This ensures if the user existed yesterday, you keep their original sign update, preventing it from being overwritten by today's data feed if it reappears. It's key for tracking state transitions, new, active, churned, maybe even resurrected accurately over time.
Very clever. Okay, one last advanced topic. Using complex data types, arrays, structs, instead of completely flat tables, especially in cloud environments. Why do this?
This tackles a major performance bottleneck in distributed systems, the shuffle. When you flatten everything out, say, exploding all of a customer's order lines into separate rows, and then you need to join that back to customer data or product data, the system often has to physically move massive amounts of data between compute nodes. That's the shuffle.
And shuffling is slow and expensive.
Very. It breaks data locality, often ruins compression benefits, and just grinds things down. The alternative, supported by modern platforms like BigQuery, Snowflake, and Spark, is to keep related data together using nested structures.
Like storing all of a customer's addresses in an array within the customer row, or order lines as an array of structees within the order row.
Exactly. By keeping related data nested, you often avoid the need for those wide joins later. Queries can work directly with the nested data. This drastically reduces shuffling, keeps data better compressed, and often simplifies downstream queries significantly. It's a more modern approach aligned with how cloud systems work best.
Wow. Okay, so from the highest level concept down to these very specific implementation patterns for history and performance, it's clear data modeling isn't just drawing boxes. It's a deep, strategic, and ongoing process.
It really is. Kimball described it like rock climbing.
Yeah.
You establish the data model, place protection. Then you verify the processing requirements against it. That's the protection. Then you enhance the model, then re-verify. It's this constant back and forth.
Can't just design it once and walk away.
Not if you want it to remain useful and performant. Successful data bending, as you call it, isn't just syntax. It's about translating fuzzy business needs into precise, scalable data structures, always thinking about how the data will be queried, even anticipating questions that haven't been asked yet.
That ability to anticipate, to build for the unknown query, that seems like the real mark of mastery.
Remember, a true data bender doesn't just manage the elements of data. They shape the flow of insight. If you don't model your data with precision, you risk losing history, breaking the grain, and ending up with a swamp instead of a well-controlled pipeline. Master the grain, and you master the flow.